let's go on to part 4 of this tutorial where we start to model non-proportional hazards. So the first question, which is question 29, asks us to allow for non-proportional hazards of age using a stratified Cox approach and interpret the results. So how we do that is, well, basically from our previous section, we've concluded that there seems to be evidence of non-proportionality for age group, and we're going to focus on that effect here and ignore any potential signs of non-proportionality for the deprivation status. So what we're going to do is, now if we're interested in a stratified Cox model, we can do that using the ST-Cox command. We still want to include our deprivation status variable in the model by using the dep variable and using the I-dot notation as before. Then we tell Stata that we want to use a stratified Cox model where the stratification is by age group by using this strata option. So if we run that, we get some output that looks like this. Now, hopefully you won't be surprised to see that there is no output for the age group here. We can see that in the output, we have strata variable age group. Now, what it's doing in the background is, as you know, the Cox model doesn't directly estimate the underlying hazard function. What it is doing, though, in this model is that it is allowing for those underlying hazard functions to change depending on age group. So the age group is allowed to have a different function. And so if there wasn't hazard ratio for those, we would allow them to change also across time. So we sort of deal with the non-proportionality of age group in the background without ever actually producing any results for that. So we would only ever want to fit such a model if we weren't interested in the effect of age group, because as you can see, we don't get any estimates of the hazard ratio for age group out. What we do get is we get the hazard ratios for the deprivation status group. So if we go on to question 30, this asks us to use ST-split to split the data set at 2 years after diagnosis of breast cancer. This is the same as what we did before in one of the previous sections. We used the ST-split command to create this variable FU for follow-up, where we looked at splitting the timescale up until 0 to 2 years and 2 to 10 years. So we're going to do the same thing here. Then what we're going to do is fit a piecewise exponential model, adjusting for deprivation group and allowing for the non-proportional hazards for age group variable. So first, let's start by doing the ST-split again. And we can see that we have created some observations as expected. When we split our data set, we now have up to 2 rows per individual. And then what we would do is, if we want to fit our exponential model, we use the ST-reg command as we've done previously. We use the dist-exp option to tell the Stata we want to use an exponential distribution. We include our deprivation variable here, I.dep, telling Stata that we have a categorical variable of deprivation. And what we do to allow for non-proportional hazards is that we include our age group variable, and we include double hashed here, telling Stata that we want to include the main effects and interaction terms with the follow-up variable. So this means that we will allow for the age group effect to change within different levels of FU. So let's just have a look what we get in our output here. So we have hazard ratios for deprivation. These do not change across our timescale. This is still assuming that the hazard ratio is constant over time for deprivation. But for age group, we get something different. So you can see that we have some main effects here of age group. We have also a main effect of the follow-up variable. And then we have the interaction term here. So if we're interested in estimating the hazard ratio within levels of the follow-up, comparing each age group to the first age group, the youngest age group, what we need to do now is have a combination of these estimates to look at that. What we can do instead is we can also predict the hazard from this model, so we can look at what the hazards look like. So if I use the predict command and predict a variable called hazard, let's do that. And then we can plot the line. We can do that now just for age group 1 and deprivation 5, just to select some. And we plot it across our timescale using the command here. So what should be clear is that we see that this is the hazard rate. We are now allowing the hazard rate to change across time. We have a hazard rate from 0 to 2 years, and then it changes at 2 years to 10 years. So we still have this flat, constant hazard rate within these time bins, but they are allowed to change across the time bins. And when we include the interaction, we also allow the hazard ratio to do this. So in the next question, what we ask is, what is the hazard ratio for age group 2 versus 1 in the first 2 years, and B, after the first 2 years? So what you should have also done is write out the model for this. So once you start to think about what the model looks like, we can start to calculate what these hazard ratios are according to our output for each of the levels within each of the different time categories. So if we're interested in estimating the hazard ratio for age group 2 versus age group 1 in the first 2 years, then we can use this lincom command and get our value out. So Stata saves our values in the background by telling us that we have something called _b, and within the output of _t, you can see here, we have the second age group. So it tells, what this means is that we basically tell Stata, okay, go into the covariate estimates _b and into the equation _t and get out the value of 2.age group. And I want you to then exponentiate this so we have a hazard ratio. So let's see what we get out. So what we get is 1.23. And this should be exactly the same as what we have here. So what this estimate, this hazard ratio for each of these age groups, these represent the hazard ratio for each of the age groups versus the youngest age group within that first 2 years. So we see that for age group 2, so I think this was 50 to 59-year-olds, the mortality rate of 50 to 59-year-olds is 1.23 times that of under 50-year-olds within the first 2 years of our follow-up, within the first 2 years since diagnosis of breast cancer. And the same thing applies to the other age groups. So if we take the eldest age group, that's above 80, we know that the mortality rate of those aged 80 plus is 4.97 times the mortality rate in those aged 50 or less within the first 2 years of follow-up after diagnosis of breast cancer. So that's within those 2 years. Now, if we want to look at the 2+ years, the 2 to 10 years, we then have to start using these variables or these estimates. So if you look at the next line of code I have here, what I do is I write out that we want to use, if we want to estimate the effect of age group 2 versus age group 1, the hazard ratio for that, within this second period, what I do is I have to take the first period and multiply it by what happens in the second period, because this is respective to the first period. But when we're on the log scale, actually this multiplication becomes a plus. So if I run this, we will get out what our hazard ratio is in the second period, so from 2 to 10 years. So actually this isn't outputted in our output here, but we should see that if we do display 1.227 times by 0.857. So what you can see here, what I'm doing is I'm taking the hazard ratio here, the value here, and this first part, 0 to 2 years, and then multiplying it by this estimate in the second. So when we're looking at 2 to 10 years, then I should get the same value as what we have here, and I do. So what this is the hazard ratio comparing the second age group, the 50 to 59-year-olds, to the under 50-year-olds within that second period. So the interpretation is that the mortality rate in those that are aged 50 to 59 is 1.05, the mortality rate of those younger than 50 within the period of 2 to 10 years after diagnosis of breast cancer. And we can do the same thing for each of the age groups. If we're interested in the fifth age group, then what we could do is we could display 4.978 times by, and then we would times it by this value, 0.8148, and we would get a hazard ratio of 4.05, meaning that the mortality rate in those aged 80 plus is 4.05 times the mortality rate in those younger than 50 when looking at the time since diagnosis of being 2 to 10 years. And we could have done this using Lincom if I just change this. I can just copy paste this across here. So if I just change this to a 5 here, when we're talking about age group, we should get the same value here. And you can see that we get 4.56. There's a little bit of difference because of the rounding. But the reason why you might want to use Lincom is because you get the confidence intervals out here as well. So if you're interested in estimating these hazard ratios and getting confidence intervals, you can get that out. Whereas looking at the output in the model and just multiplying these values, you wouldn't get the confidence intervals. So that should be really clear then that what we've got now is we've got a model where we actually have hazard ratios that change over time because we have a different hazard ratio within that 0 to 2 years and that 2 to 10 years. So what we might want to do, what we didn't do in the third section, is actually test for an interaction of these two variables to see if there's evidence of non-proportionality. So if we were still unsure from looking at our output previously, when we looked at the log-log plots, which weren't extremely clear, and we looked at the predicted versus observed survival, and then we performed this Schoenfeld residuals global test, and we said that it can be difficult because you may have, within these different groups, we have different p-values which may indicate or not indicate non-proportionality. So one thing that you could do is you could actually fit a model including this interaction with time and see whether, okay, does that significantly explain more variability in our data? Let's see that here. So what we're going to do now is we are going to use our Cox model, or is our SD-Reg model, sorry, our exponential model. So I'll just reread that in so you know which model we're looking at. And then what we want to say is it worthwhile basically including these in our model? And if it isn't, then that would indicate that proportional hazards is actually an okay assumption. So we can do that using the test parm command in Stata. And we basically tell Stata, we want to test in this model, does the combined effect of all of these individual variables, these individual interactions, is that significant in our model? Because we can see from the output that probably it will be, because all of the individual interaction terms are highly significant. But let's just run it and have a look. So what you can see that it's doing is it's testing these hypotheses together that the covariate values here estimated are significantly different from 0. So if we see that they are significantly different from 0, then that would indicate that we need them in the model, meaning that we need to include the interaction, i.e. proportional hazards isn't a reasonable assumption. We want to allow these hazard ratios to change across the time scale. If we see that these are not significantly different from 0, then basically we can set all of the covariate coefficient values to be equal to 0, meaning that we don't need them in the model, and that we can allow for proportional hazards. But here we see that the p-value for this test is really significant, not really surprising looking at the output for the different wall tests in the output in the model. But that means that we cannot conclude that these coefficients for these interaction terms are significantly different from 0, i.e. we need to include them in the model. There's evidence that there is non-proportional hazards. So the last part of this question asks us to use the ST-split data set to estimate a non-proportional hazards Cox regression model, as in question 31, using ST-Cox command. Note also that it's possible to estimate this using the TVC and TX options. But for this example, it takes a while to run, so I haven't actually written this here. But if you go back to the slides, you should be able to see how the format or the how you write this in Stata. And then you can run this, but it will take a while to run. So what we do instead is we fit the same model using the same interaction terms using the ST-Cox model here. And we can see again that we get estimates of the hazard ratios here for the age group. And this is what happens in the 0 to 2 years. So we can see that we have, if we take the 5th age group, the mortality rate for the eldest age group versus the youngest age group is 4.8 times. So the mortality rate in the eldest is 4.8 times that in the youngest within 0 to 2 years after diagnosis. And then if we want to get that value within the 2 to 10 years, we again just do the same thing as what we did before, or we can use the lincon command to get confidence intervals too, but we would do 4.80 times by a 0.814. And we would get another hazard ratio. This would indicate that the mortality rate in the eldest population is 3.9 times that in the youngest population within the time frame of 2 to 10 years after diagnosis. So again, we allow for the hazard ratios to change across the timescale.